Yeah, I guess that's probably a good idea. Uh-oh. Oh, yeah. Quiz people after school. Yeah. You probably still have to remind me tomorrow because
I forgot about it too.
I did too. So, all right. So, just reviewing what we discussed yesterday, the ideal gas equation, where we essentially took the three first gas laws and related them together. And so that's what we're going to kind of focus on in question number 4 here. Okay. So I'm just going to get us to a point where we've already gotten to, and then we're going to go over number 4 here. Number 4 is pretty straight and narrow here in terms of, how we go about solving this. Camden, can you see that? Okay. All right. So number 4 says, if 4 moles of a gas at a pressure of 5.4 atmospheres have a volume of 120,000 milliliters, what is the temperature? So we are given moles, we're given pressure, we're given volume. So having all of those, one of the key ones to tell us which formula we're using is the fact that it says moles. Okay, so that means we are going to use Pivnert, and we're going to solve for T. All right, so let's again list what we know. Okay, we've got pressure, we've got volume, we've got N, we've got R, and we've got T, which we are trying to solve for. Okay, what's our pressure in this question? 5.4 ATM. Do I need to convert atmospheres to any other unit, or am I good? I'm good. I'm good, you're good. Volume. What do I have for volume? 120,000 milliliters, but is that the appropriate unit, or we need to convert? We need to convert to liters. So take the 120,000 milliliters, divide it by 1,000. We have 120 liters. N, moles. 4. And who can give me the numerical value of R?
0.08206.
Very good. You are correct. And the unit for that is liters times atmospheres per mole times Kelvin. So, taking the Pivnert equation and solving for T, we're going to have PV over NR. And so what I want you to do is I want you to plug in the values, solve for it, and provide the appropriate unit in your response.
It is that big. Okay. Right.
Think about it, the volume itself, to think about 5.4 atmospheres, that's an incredible amount of pressure, honestly, to have in a container like that.
Do you know what it is on like the surface of Venus? I know it's a lot higher.
Off the top of my head, I do not know. But yeah, I've heard the same thing, that it's like we really couldn't go there if we had the option, unless we had the correct vessel.
I think it would be cool to have, like,
It would be. Yeah, because it's so pressurized and dense that we couldn't really get to where we wanted to on all the way to the surface. So we should get 1,974 Kelvin. Is that what everybody got? Okay. Well, that takes care of the worksheet. Again, hold on to it. Next, we're going to take a quick gander at a slide that is going to show us some previous formulas, also some new ones. So you got your Charles law, you got your Boyle's law. Again, those really only take a look at how temperature or pressure affect volume. Okay. Well, what would happen if we changed more than one of those variables, where we took a look at how does temperature and pressure affect the overall volume of a gas? That's what we call a combined gas law. So oftentimes, again, these are really all related to a form of Pivnert, but if you look at here, besides R, what is missing? N. So oftentimes the amount of the gas is held constant. Okay. And this last formula doesn't really have a name. So I just call it the additional formula. And that's when we take a look at how does temperature affect pressure when volume is constant. Okay. So you're going to see over the next couple of problems that the book has a way of organizing information. They put it in table form. But honestly, it's really not any different than what we do when we list what we know on the side. So you can kind of pick and choose what you want to do. But again, we've been doing this all year long. You know, if you want to change ways, that's fine. Now, what I plan on doing is this. For these next two questions, or next two samples, I am going to go over the practice exercises only. Okay. The sample questions for each of the next two types of problems are pretty similar to what we're going to be doing. And they're already solved for you. So I encourage you to read over them just so you can see, you know, a new question. But again, I'm going to focus on doing the ones where we do them together. Okay. So here on this next practice, we're going to be taking a look at calculating the effect of temperature changes on pressure. Okay. So we have a natural gas tank, and the pressure is going to be maintained at 2.20 atmosphere. On a day when the temperature is negative 15 degrees Celsius, the volume of a gas in the tank is 3.25 times 10 to the third meters cubed. What is the volume of the same quantity of gas on a day when the temperature is 31 degrees Celsius? So let's evaluate this question. What can we say is being held constant? Pressure. And what else? Moles. So pressure and moles. So what is changing? Volume temperature. Okay. What law can we relate that to? What now? Bingo. Charles's. So Charles's law, V1 over T1 equals V2 over T2. And what are we solving for here?
Volume, final volume.
Final volume, perfect. So, and I'll show you the table setup on the next question here. I meant to do so, but then I got so excited about doing this problem that I just forgot. So V1, T1, V2, T2. Okay. V2 is what we're solving for. What's my initial volume?
25 times 10 to the third meters cubed.
Now, I'm going to say this. For this particular unit of volume, it is perfectly acceptable. Okay. And we're going to leave it in that because adjusting for that, we don't need to adjust for that. Okay. The steps that are involved, it's unnecessary. We can keep it. It's an appropriate unit. Okay. But I do like always changing the temperature to Kelvin. So what was my initial temperature? And so to find Kelvin, we add 273 to that. What do we get? 258. What was my second temperature?
31 degrees Celsius. 304 degrees, or 304 Kelvin.
304 Kelvin. So again, you can put the numbers in as is or rearrange the formula. But if you rearrange the formula right off the bat, you get V2 is equal to V1 T2 over T1. So like before, enter the numbers, calculate it. Don't forget that the initial volume, has the 10 to the third in there. So you want to make sure you put your parentheses in your calculator, tell it what to do. And I also want you to report your answer in scientific notation. Camden, may you please provide an answer? I'm gonna.
Oh, no negatives?
No negatives. No negatives. Colin.
3.83.
Did you get it the second time?
You need a little finagle over here.
Oh, I'm not going anywhere until I make sure we get it punched in your calculator correctly. You get it?
No.
Okay, so let's set this up for you. Okay, so V1 was the 3.25 times 10 to the third meters cubed. Okay, T2 is the 31 plus 273, 304 Kelvin. All over.
Sorry, I use Celsius. That's what
Oh, that had to been hard to say.
273.
273.
270.
So you add 273 to your degrees of Celsius to convert. You get her now? We got time. We'll stare at you.
Don't worry about it.
Yeah, worm guts. Yeah, don't forget we're recording, so whatever you say is evidence.
I didn't do it.
Plead the fifth.
Yep.
You got her? I know, right? All right. Now, let's ramp her up a little bit. Okay. So now is when we are going to take a look at the effect of changing both pressure and temperature on volume. Okay. And so again, just kind of go through here real quick, but you see here, I wanted to show you, the table setup they have here where they have initial, final, pressure, volume, temperature. We do essentially the same thing. We just don't put it in table format. Okay. All right. let's look at this question, shall we? I'm gonna give you a little piece of advice. You want to make sure you have plenty of room for this one. Okay. Let's proceed. A 0.50 mole sample of oxygen gas is confined at 0 degrees Celsius and 1 atmosphere in a cylinder with a movable piston. The piston compresses the gas so that the final volume is half the initial volume of the final, and the final pressure is 2.2 atmospheres. What is the final temperature of the gas in degrees Celsius? Lots of words in that one, isn't there?
Are there any like this on the top?
There could be. There could be. That's kind of why I gave that slide with the additional problem or formulas on there a couple slides ago. Now, when we work through this, you're going to be like, okay, it's not as terrible as it seems. It just has some additional steps, okay? And the steps aren't anything new. So let's start breaking this down, okay? Is there anything being held constant? N, the number of moles of the sample. So, and what is changing? Pressure. I bet you there's other things too. Temperature. Bet you there's other thing too. Volume. Okay. So N is being held constant. We've got P, V, and T changing. So the formula that we need to use is going to be that combined gas law, where it is P1 V1 over T1 equal to P2 V2 over T2. And what are we trying to solve for? Final temperature, so T2. Okay? All right. Get the brain and the hands ready. Listing what we know. P1, V1, T1, P2, V2, T2. T2 is what we're looking for. Okay. What is my initial pressure? 1 atm. What is my initial volume? Let's come back to this one. What's my initial temperature? So 0 degrees Celsius into Kelvin. Okay. What's my my final pressure? We are trying to find T2. And do we know what our final volume is? What's that? Or half the initial. So we are missing some information. We are not told what our volume is directly. But what we can do and what we do know is, A, we can use our initial information because we're given enough initial information as well as the number of moles present. So in order to find the initial volume, we need to take PivNert and solve for V1. So V1 is equal to nRT over P. Again, that's going to be T1 and P1 that we use. So go ahead, and you can follow along with me if you want to. V1 is equal to 0.5 mole, R 0.0206, and for space-saving measures, I'm not going to include the units, okay? Our T1 was 273 Kelvin, and our P1 was 1 atmosphere. So what is our initial volume?
11.2.
Very good. What, the number or the unit?
The unit.
Oh, okay. I was like, if you guessed 11.2,
Yeah, that'd be impressive. I'm not that good.
you probably are.
Fine.
All right, so we've got our initial volume now. Now, Colin, what's going to be our final volume? 5.6, because we said that we compress it to half of the initial volume. Okay.
We are due. Is it 0.8?
Thank you.
Oh. No, I mean, I really couldn't see. I didn't mean to.
Oh, yes. I mean,
Okay.
oh my gosh. I'm just making this worse. No, I had it right the whole time. Yeah, I sure did. 0.08206. This is why I like doing stuff on the board. Since I made a boo-boo first hour. What's that? What was your question, Adam? Yeah, that's me. I'm I'm the same. I am that way. All right. So now we used PivNert to get our volumes. And now we can go back to our combined gas law formula and we can solve for this. So rearranging this to solve for T2, we eventually end up with T2 is equal to P2 times V2 times T1 all over P1 times V1. Lots of moving pieces in that one. So now we can go ahead and plug in the known values. Let me give you a few moments to type them. Hello. This is what we're doing an intro today.
Looks pretty easy.
Mhm.
You know all the numbers.
But we weren't given all the numbers. We had to figure them out.
It's not that hard.
Well, you're the dean.
It's just called algebra.
You're the dean.
It's hanging on.
Savannah, you got an answer?
I don't know if it's right, but I got 37,669.6. Yeah, I don't think I did it
I
right.
got 300 Kelvin and 27 degrees Celsius.
Yes. So we're going to come back to you, Savannah. So we have 300 Kelvin for our temperature. But again, the problem says we have to answer in terms of Celsius.
I don't know if you do that.
What's that?
With Celsius.
Okay.
You
So
put in your calculator different?
so let's ask this question. Are you going from Celsius to Kelvin? Is that where the
Well, I just plugged in the numbers. Like, that's it. That's all I did.
Okay. So let's go and see what numbers are going where. Okay. So we should have T2 is equal to P2, which is 2.2 atmospheres. Okay. V2 was 5.6 liters, and T1 was 273 Kelvin. Okay, that's all on top. P1 was 1 atmosphere, and V1 was 11.2 liters. Okay. So take your top, multiply them together, and divide that by 11.2. So, okay, 300 Kelvin, okay, which is what we should get for Kelvin. But in order to calculate our answer in Celsius, we have to take that conversion factor into account. So in order to go from degrees Celsius to Kelvin, you have to take whatever degrees Celsius you have and add 273. Okay?
Answer plus that.
Well, our final answer in terms of Celsius, we have to go backwards. So we're going to go from Kelvin to Celsius, and we're going to use the subtraction. So we're going to take 300 Kelvin minus 273. $27, you got it. So did you jot down how to convert?
Yeah.
Okay, good, good. Okay, I'll leave that up. You're good? Okay. Starting in section 5, which we're going to dabble in on Friday, we get into densities of gases. And then we're eventually going to get into my other favorite formula in this chapter, but I'm going to save that and build suspense for you until we get there. Cliffhangers, always got to have something to look forward to, right? All right. So, again, you've got your quiz tomorrow, partner quiz.